Okay, are you ready? Well, let me just start at the beginning. And actually, I'm not gonna start at the beginning. I'm gonna go back for 5 years. It was this comparable meeting 5 years ago, the first one that got canceled because of COVID. We were all set to be here and UT closed the campus. So that was before we had all Zoom set up. So we just totally missed that meeting. But it's just amazing to me that it's been 5 years, but yes. And speaking of COVID, as Jamie said earlier, most of you heard, I think, our speaker for tonight, Lindsay House was, she was going to talk about her project where she works with doing a citizen science effort to look at dark energy, dark matter. I'm not sure which or both, but she had emailed me today to say that she had COVID. So I was thinking we were going to have a program. I sent out an email and our wonderful, reliable friend, Bill Spizzirri, said, I could do something. So yes, Bill, we will greatly appreciate that. So Bill has done a lot of programs for us, very interesting. And he is back again tonight on very short notice. And so take it away, Bill.
Okay.
Are we sharing?
Thank you. I'll try to do this kind of last minute setup here. I appreciate your concern that I can't be there for pie, but my wife made pineapple upside down cake, so I'll be okay. Oh, by the way, this is her birthday today, Pie Day, and maybe some of you know Albert Einstein's birthday too. Anyway, okay, so I have to share my screen, or correct? I'm pressing a button. I see, I'm going to try to do this. There's that. Hold on 1 second. I got to get rid of these thingamabobs here. Okay, I did that. Slideshow. Come on, here we go from current slide. I'm hoping you can see the Steward Observatory Mirror Lab slide. Anybody?
Yeah, we can
Okay.
see it.
All right. The reason in the late 1990s, my daughter was looking for a place to go to college. She was thinking about the University of Arizona. We went to go there, visit there to check it out. I heard that they had a telescope mirror lab there, so I wanted to check that out. That's how I got the opportunity to see this. Now, in this picture, it's difficult to tell, but maybe you can tell. This is the exterior of the football stadium at the University of Arizona, and that's where the mirror lab is, underneath the football stadium. Why is it there? I don't know. They probably got a good deal on the property. So what's a telescope mirror? I'm going to try to get through this real quick. I know you guys, a lot of you know this, but this is how my presentation was set up. First of all, you have a typical refractor telescope. That's a tube with a big lens in the front, so the light from the image can come in, and then a small lens in the back that focuses the light, and that's called the eyepiece. And that's a refractor. There's no mirror in it, okay? And then there's the reflector telescope. It also has a tube, the light comes in the front, and then there is a concave mirror in the back that reflects the light to another flat mirror that reflects the light up to the eyepiece, the small lens over here, okay? So that's the reflector. It uses a mirror, not a lens, okay? That's probably not news to a lot of you. So how do you make a mirror? Here it is in 60 seconds, okay? First, you take a piece of flat glass. This one's about 7 inches in diameter. And, you know, there's good glass and there's cheap glass and there's better glass and all that. But let's just say you use a piece of glass. And then you have this tool, this weird looking tool, which has an extremely rough surface. And then on that surface, you put a grinding powder, okay? And then you spend 8, 10, 12 hours rubbing your glass against this grinding tool with the grinding powder to shape the mirror just right in a parabolic shape so that it reflects the light properly in a reflecting telescope, all right? That's what I knew about making mirrors back then. And in this picture here, you can see this flat thing is resting along the edges of the mirror. and the mirror is no longer flat. It's got a parabolic curve to it. And that takes many, many hours of grinding if you're making your own mirror, okay? And so a small mirror takes many hours. So if you're making a big mirror, it's a problem. Then after you get your mirror the correct shape and super polished, very smooth, you put it in the, by the way, can you guys see my cursor?
Yes.
Anybody?
Yes, we can see
Yeah,
it.
okay, so you put your mirror right about over here where you see the silver stack, okay? And then this silver cylinder comes down and makes this a vacuum chamber, right? So they pull all the air out of it, and then, but your mirror is in here, all right? And then they put a very small piece, I think it's like a piece of tinfoil shape size of aluminum inside the vacuum chamber with your nice polished mirror. You take all the air out, and then they heat that piece of aluminum. It forms a fog, a cloud of aluminum in the vacuum chamber, and that aluminum fog goes down onto the surface of your mirror, it sticks to it, and now you've got a perfectly shaped, perfectly smooth mirror, and now it's perfectly shiny because of the aluminum coating. The aluminum coating is just a few molecules of aluminum, but this is what they coat mirrors with nowadays. So you end up with something like this. Look at that thing. It's a perfect mirror, okay? It's super smooth, parabolic, and aluminum surface. So telescope history real quick. So 1609, Galileo had a 2-inch telescope. He changed the world with it, right? It was a refractor, so it had a lens on one side, a lens on the other, and he discovered the moons of Jupiter and the phases of Venus and lots of other stuff. And then, of course, you guys may be familiar with this. People always want a bigger telescope, right?
Yeah.
So those refractors got bigger and bigger and bigger and bigger. This is a very short story here. Until the biggest one was made by the fellow with the beard in the middle over there. His name is Alvin Clark. He was a master craftsman of making mirrors. And he made a 40-inch mirror that was used in the Yerkes Observatory, which is on the southern border of Wisconsin, very near Chicago. It was the biggest telescope in the world when he made it. I got a chance to look through it because I was living in Chicago most of my life. And it, of course, is a masterpiece, absolutely beautiful optics. And it's still working there. Now, they don't do research there anymore, but it's there, and the public goes in, I think, just about every clear weekend. Here's the Yerkes Observatory dome on the left. There's the telescope on the right, 40-inch lens in the front. So that's what it looks like. And you know, when you look at lenses close up, they just don't look really amazing, but that's the 40-inch mirror at Yerkes. And it's great because, you know, it's a very old-fashioned piece of hardware. And if you want to point it at something, you just grab the bottom of the telescope and you heave it over and point it to wherever you want to point it. Anyway, so that's the 40-inch mirror. Now that's the biggest refractor at the time. It's the biggest refractor lens today. People have tried to make bigger ones and they never worked. So that is still the biggest lens that ever made for refractor. Then you heard of this really smart guy, Isaac Newton, who studied light, many different aspects of light. And he learned that when the light goes through a lens and a refractor, it gets distorted. Okay, here's this is either one of the ones he made or a model of it. I'm not exactly sure. 1.3 inches in diameter, the objective, 1668. Okay, and so he said because light gets distorted through a lens, because he studied light, he said you can use a mirror with the right shape instead. He invented the reflector telescope. So then again, we're going to go through this really fast. Everybody wants a bigger mirror, bigger, 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 bigger all the time. And in 1917, George Hale, a big rich guy who wanted to do astronomy, financed a 100-inch mirror, 2.5 meters, to go on Mount Wilson, California, which is still there. I'm pretty sure it's still there.
Yeah.
1948, I think he wanted to make a 300 or 400-inch, but anyway, nobody could agree to do that. So they built a 200-inch telescope, which went online in 1948, sitting on Mount Palomar. That's 5 meters across. And that was the biggest telescope in the world in 1948, and it remained the biggest in the world until the Keck telescopes were made in the early 90s on top of Mauna Kea on Hawaii. Anyway, so here's Mount Palomar, 5 meters. I got to visit it there. That's another presentation I could give you. I got to visit there in 1993, 94. Got to talk to the astronomers. It was fantastic. So this is the dome on the left. Now, this picture on the right looks like this tube here is the telescope, but it is not. The 200-inch mirror sits down over here on the bottom, if you can see my cursor. And then there's no tube as such. It's an open truss design. And this is the prime focus, or sometimes they use a Cassegrain. But anyway, so usually the prime focus, this is where the cameras are, etc. Nobody looks through a eyepiece on a 200-inch. Here is the 5 meter as it was being made back in the 1940s. As you can see, it's big, it's smooth, and they had to use the technology of the day and get creative to make this giant thing, right? Here's a picture of it with newly illuminized, because they have the equipment to do the illuminizing in the big observatory dome, and they do that every 5 years, I think, something like that, to keep it working good. 23 inches thick, 14.5 tons, because they just used to make solid mirrors back then. So they said, boy, that's a big mirror. We cannot possibly make a bigger one. Why? It's too big to cast. It's too much to grind. The Palomar mirror is 10,000 pounds. It's too heavy to ship. If you made it in Europe or someplace else in America, it's too heavy to ship. The mount for such a giant mirror would be too big, expensive, and heavy. It was so heavy you wouldn't be able to focus it. And of course, all that together means it's going to cost too much money. All right, then 1985, a guy by the name of Roger Angel came up with this idea. He said, have you ever noticed if you take a container full of liquid and you spin it, the centrifugal force pushes the liquid to the side, and the liquid makes a really nice curve. And if you have just the right container and you spin it just the right speed, you can make it just the curve you want. And that saves an awful lot of time and expense and glass to make a telescope mirror. And there goes my light. That's okay. I shouldn't hit the desk like that. I assume you can still hear me, right?
Yeah, we can.
You don't want to see me anyway. It's not worth it. Okay. So he said it's really simple to make a mirror like that. 3 simple steps. You melt the glass, you spin it, and then you cool it. Easy, right? So he said, let's make a big one. So he started to make 6 meter mirrors this way in the 80s, okay, or maybe the early 90s. I'm not exactly sure when he did his first one. And then I'll give you a heads up. He started to make 8 meter mirrors. You'll see some of that later. All right. Now, why is everything measured in meters? Because all the countries that you see in green on this map use meters instead of feet and inches and miles, etc. Okay, they use kilometers and meters. Only in the United States, Antarctica, I think this is Myanmar, and one country in West Africa uses the kind of measurement that we use in the United States. So everything's in meters. Anyway, so that's called a metric as opposed to what we do in America, imperial. Okay, so they have to put the glass in a giant oven that spins, okay? This, I believe, is the oven that they used for 6 meter mirrors, I think. And so as you can see, this is a tricky piece of technology. It's got to come up to, I think you'll see later, it's got to get really hot, it's got to be sealed, and it's got to spin at just the right speed for a long period of time. That's what the oven looks like. Here's what it looks like inside the oven. You see the guy, so you get an idea how big it is. Now, all these squiggly lines all over the top and the sides, these are heater coils. This is how the heat gets into the oven and to melt the glass, okay? And here's a view where the top of the oven is off, and they're putting these ceramic cylinders in there, and each of them is attached by a ceramic bolt to each other, so they stay in exactly the right place. As you can see, the ones in the middle have a cover on them. All of them eventually have a cover on them, and they put a whole bunch of these inside the oven before they put the glass in it, okay, so that the glass does not go in those areas, which means the mirror is going to be much lighter and use much less glass. The cylinders come out later. I'll explain that to you. So and not only are they going to be doing the heat it, cool it, spin it, and cool it, but they're going to make it hollow on the inside. All right. So it's super, super light. That means its mount is smaller. That means it's lighter. It's cheaper. Less glass. It's the only way to go. So these guys have put these cylinders in there. They're ceramic. Here's a close-up of them. So this is a cylinder that's cut in half. First of all, it's really two cylinders. They're connected with each other with bolts, these ceramic bolts, so that they absolutely positively don't move during the spinning process, right? And then this one on the right is cut in half so you can see that it's empty, all right? And when they pour it, when the glass is melted, it obviously covers the top of these cylinders, and then glass falls in between, maybe about a centimeter of glass between them, and then there's glass underneath them. So it makes kind of like an I-beam, if you can understand that, okay? Glass on the top, glass on the bottom, and glass in between each cylinder, which makes it stronger, okay? Everything's empty where the cylinders are, but this way the mirror is nice and strong. Here's another view of the cylinders, the covered ones, the uncovered ones. In this particular mirror, so over 1,700 cores to keep most of the mirror empty, to keep it light. Here's the guys, after all the cylinders are in, these guys spend a couple of days putting chunks of glass, this special Japanese Duro glass or something. I forget what it is. I don't know if you can, when I was there, I got a really nice private tour, okay? And I saw the pieces of glass and I said, boy, you know, it'd really be nice if I could take a piece of glass home. And he says, no, I can't let you have that. He says, what about if I give a donation to the observatory? And he just looked at me with this stupid look on him. He says, oh, good, here, just take a piece. So, you know, you got to make a frowny face. And anyway, so, you know, you're not seeing this too much on the Zoom here, but I just got a piece of glass. And it's not that big. Look at next to my head. It's very small. Okay, so anyway, that's the piece. Those are the pieces of glass. They put tons of this glass on there by hand to get things started. And again, there it is. O'Hara E6 Japanese glass. What does all that mean? I don't know. Anyway, so that piece is bigger than mine. So then you put the glass in. You put the cover of the furnace, the cover of the oven back on. You heat it to 2,100 degrees Fahrenheit. You spin it at 7.4 revolutions per minute for 4 days. That both melts the glass and puts it on the special parabolic curve. I'm thinking they must have practiced an awful lot before they got that just right. The glass ends up to be about as thick as honey. And again, as you saw, the glass starts out to the top, but then when it's melted, it goes down in between the cores. So some of it stays on top of the core, underneath the cores, and in between the cores, okay? And voila, or ta-da, you end up with an amazing piece of hardware, okay? Now, again, it looks solid, but it's mostly empty underneath there because of the cores. By the way, the cores get taken out later with high pressure water from the back of the mirror. So they're gone completely after a while. But you can get an idea, you see the people, you get an idea how big the doggone thing is. I'm surprised that lady on the right is allowed to touch it, but that's the way it goes. Anyway, so then after it's the right shape, because of the spinning, they have these computer polishers. And each of these pieces here, if you can see them, are constantly being adjusted so that they polish this thing absolutely perfectly. This is obviously a piece of technology that they developed here at the lab, and doggone it, they make really nice mirrors. Okay, what else can I tell you? They got fancy technology. This is a picture I took, and I was shocked. This was a 6.5 meter mirror, and these two people were laying down on the surface of this brand new perfect mirror. And they were using something that I think was like a pencil eraser and some liquid, maybe distilled water, I'm not sure, to take care of extremely minor problems on the surface of the mirror. For instance, they said one of the things they mentioned was a bubble that might have occurred, a very tiny bubble on the surface of the mirror. They got to get rid of it, okay? And this is how they do it. They just lay down on the job. Here is the mirror. After it's, I have videos that show you some of the stuff. I don't know if I'll be able to show you tonight because I haven't had a chance to put them all together, but you see this guy in the middle, this guy over here, so you can see how big they are, okay? How big the mirror is, right? And what happens is the mirror is in the oven. It's all ready to come out of the oven. They take the top of the oven off, and then and this scares the heck out of me, they glue these big round discs to the surface of the mirror, which really frightens me. And that's what they use to pick the mirror up and put it in this big cell, mirror holder, whatever you want to call it. And then they can put it on the side. When I was there, they had several of them laying vertically like this that they were doing various work on. And then after it's all done, you've got to take it from the University of Arizona to whatever telescope's going to. Sometimes someplace else in Arizona, California. Some of these are going to the mountaintops in Chile. And as you can see, it's tricky. You know, you want a guy who can really drive a truck well, I guess, and it's going to block the road. So they're going through an awful lot of trouble. Why do they do it this way? The spin, I tried to mention this before, the spinning eliminates tons of grinding, okay? So that saves a lot of time and a lot of money. And as you saw with the cylinders that keep the mirror hollow, they use a lot less glass. That saves more money, okay? The hollow mirror is about 1/6 the weight of a solid one. So this is a great way to do it. It's easier to transport. It uses less glass. It allows them to use adaptive optics because the mirror is thin enough to be flexible. If you're familiar with adaptive optics, where they can flex the mirror according to the way the atmosphere is behaving. Okay, they get better images. Also, since there's less glass, this mirror will reach equilibrium. That means it will reach the same temperature as the surrounding air, so you'll get better images, okay? When the mirror is lighter, you can make a lighter mount, saves more money. It permits the lighter mount means a smaller dome, saves more money. So this might look like an awful lot of crazy work to do, but it has many, many benefits. So 6.5 meter mirrors, there's a picture of one. It went in the multiple mirror telescope in 1992, and then again in 2000 they changed it. But anyway, the Magellan 1 telescope in 94, the Magellan 2 telescope in 1998, a Lockheed Martin telescope, which I think was military, in 2002. So they've made a lot of these mirrors, and they're extremely successful with it, right? And this is the interesting part. So somebody came up with the idea, look at this, we make 6 mirrors. We call it the multiple mirror telescope. It's on a mountaintop in Arizona. I forget the name, 1992. And then they said, hey, you know what, man, that's great. 6 mirrors, you got a great telescope, but we can make you a 6.5 meter and make your telescope much, much simpler. And so the multiple mirror telescope is no longer multiple. It just has one big 6 meter mirror, but they still call it that. That's the mirror for the multiple mirror telescope. If you look closely, you can see the parabolic curve in the surface of the mirror there, if you look closely. There is the same multiple mirror telescope with the single mirror in it. Here's the Magellan, the 1 and 2. I think they're in South America on a mountaintop in Chile, I think. And they've got 6.5 meter mirrors. And that's what they look like close up. Obviously, this is the, maybe for Casa Grande or maybe the prime focus, I'm not exactly sure. Anyway, then they started making 8.4 meter mirrors. You know how astronomers are, they always want bigger ones. The Large Binocular Telescope in 1997, the Large Binocular number 2 in 2000, the Giant Magellan 2005. I will tell you more about the Magellan telescopes in a while. The LSST, Large Synoptic Survey Telescope, which I believe was just changed. It's got the name of a lady astronomer on it now instead of LSST. It's a survey telescope, as the name suggests, where they can take the entire sky, I think twice a night, of this telescope. we'll talk about it more later. And then there's the Giant Magellan 2 and the 3 and the 4 in 2012, 2013. So they're using all these 8-meter mirrors. They're making them like crazy. Here's an 8.4 meter mirror compared to what is called a normal human being. They're just really big, okay? Amazing pieces of technology. And then of course, when it's an 8-meter mirror, it blocks 3 full lanes on the highway. Don't get into an accident. And this is the way they have to do it. Another way they can ship these mirrors around is like this. Only takes 2 lanes, fine. Now here is the so-called large binocular 1 and 2. The mirrors were cast in 2004 and it was up and running in 2006. It's just a diagram, of course. A really big set of binoculars, okay? With the 8-meter mirrors. There it is. So the 2 of them together give you the equivalent of approximately an 11.8 meter mirror. All right, so big telescope. Then I mentioned before the LSST. God, I can't remember what it's named now. It's named after that lady astronomer. Darn it, try to remember. It has a 3-degree field. Remember, the moon is a half a degree. So this is the diameter of this field of this telescope, because the survey telescope, 6 times the moon. At the time, the biggest camera, 32,000 megapixels, okay? So it's got an 8-meter primary, but the primary is really just this tan exterior here, okay? Then, so the light comes in, bounces off the exterior of the primary, bounces up to the secondary, you see, which was also made at University of Arizona. That light bounces down to the center portion of the primary, which is ground differently, different curve, okay? And then that light bounces up to where the sensors, cameras, etc. are, okay? So it's a primary mirror, a secondary mirror, 3.4 meters, and a so-called tertiary mirror of 5 meters in the middle of the primary, although the primary and the tertiary were made out of 1 piece of glass. I don't know what smart guys figured this out, but that's what they do. And the LSST, I think I'm going to tell you, has just come online. So, and here's that primary. You can see the primary mirror on the circumference, and then the tertiary mirror, completely different angle in the middle. So this is a very creative idea. Okay? And it gives you an idea of the field of view of the LSST. There's the moon. Now, normally you take one of your telescopes and you look at the moon, you're going to see a very small part of it. The Hubble telescope will show you a couple tiny craters, right? But the LSST is made as a survey telescope to look at the whole sky every night. So different optics. Maybe that's correct. Well, it's got a question mark. I don't know. I looked this up just the other day, doggone it. Anyway, I think it's operational now. Oh no, this July, the LSST, and whatever it's called, is going to be operational. So then there is this thing called the Giant Magellan Telescope. It's not going to have an 8.4 meter mirror. It's going to have 7 of them, okay? Equivalent to a 24.5 meter mirror. That's nuts. Each one's 20 tons, 10 times the resolution of the Hubble. It will be, they say, the most powerful telescope in the world. So you think you got a big one? Yeah, well, here we go. This is what it's going to look like. And you may notice this here, cue the dramatic 2001 Space Odyssey music, because this thing is really big, okay? 7 mirrors, each one 8.4 4 meters. Here's the secondary up here. And then it's got a Cassegrain focus down here. And all of this, it's inside the observatory dome, and it's got all these windows to let the air go through to equalize the temperature when they're observing, right? And all of these mirrors are being made at the Mirror Lab at the University of Arizona. I believe they've completed 5 of them. I meant to, things got kind of busy today. They're very close to making the last mirrors. And so this will be a couple of years before it's operational. This is what it'll look like on a mountaintop in Chile. Everybody, you got a big scope. Everybody wants to put it on the mountaintops in Chile. It's a desert over there. There's no moisture in the air. They're at 16,000 feet, I think. So they're above an awful lot of air. So, even with adaptive optics, then you get great views, really nice images. Here's a diagram. Here's a diagram that where did I find this? I don't remember. Remember how the Hubble was so great? This is the mirror of the Hubble telescope. I forget how many inches it is, 20 or 30 something. And then here's the James Webb. Look at this, planned for 2018. So this is an old diagram, okay? James Webb, it's made out of pieces of mirrors, not one mirror, made out of pieces, right? Much bigger than the Hubble. And then here is, let's see, the Magellan's telescopes, the 6-meter mirrors. Here's the very large, a very large telescope. I forget which one this is. 8-meter mirrors. The large binocular with 2 8-meter mirrors. This circle shows the equivalent of what the 2 meters gives, together. Hobby Everly. This is the, you know what this is? The Hobby telescope in West Texas. McDonald Observatory. Sorry. Lots of other telescopes. Some of them are single mirrors. Some of them are like the Keck telescope, made out of many segments. There's a Keck 1 and the Keck 2, and they have made out of many hexagonal segments, okay? Now, and then here is, compared to all of these, the giant Magellan with the 7 8-meter mirrors, okay? Now, these two things, the 30-meter telescope and the European extremely large telescope, I think they got canceled. I don't know. They're not happening this weekend, that's for sure. And then, you see this gray circle here? If you can follow my cursor?
Yeah.
An idea that some person had for what they call the overwhelmingly large telescope, which I think, what else you're going to call it, right? And where do you make that? Well, it's got to be segmented like these other big ones. You just can't make a mirror that big. And it says underneath it over here, canceled. I'm not surprised. Anyway, and I own a C8 telescope, a Celestron 8-inch. And there is how my C8 compares to the rest of these mirrors, okay? I consider my C8 to be a nice big telescope, but you can barely see the dot over there. Okay. Videos. All right.
Not really good at naming things. They're not very imaginative.
Do I have more time?
Wouldn't get canceled.
Yeah, right.
Okay, here's the deal. I'm going to stop sharing. I don't know if I'm going to be able to do this. The videos are very tricky. These videos I made in the 90s, and they don't work well. I can't even get there now. I don't know what the problem is. They're really not important. You see the oven spinning. You see a close-up of those cylinders. You see me trying to bribe the guy to get my piece of glass. Okay. He ended up not taking any money, so God bless him. The thing is, Roger Angel had a vision. The man, we had a problem making big mirrors. He had a vision. He was a smart guy. And not only that, he made it work. There was a lot of money there. There was a lot of people at the university to convince. But now, that was in the 80s, mirror after mirror after mirror after mirror. They're making the big ones in the world, period. And when I say the biggest ones, I mean the biggest one-piece mirrors. If you want to do like the Keck and make 40 or 50 segments, yeah, you can do it. And of course, there's a lot of reasons to do that. And maybe it's just plain a lot easier, but that's about all I can tell you, I think. I think I showed you everything I can. So thank you very much for your time and attention. If somebody's sleeping next to you, hit them with your elbow. And if there's any questions or anything, please let me know.
Bill, can you hear us? Can you hear me?
Yes, I can. Go ahead.
Awesome. Well, I just want to say thank you for coming up with this at the very last minute.
Yes.
And so you can be forgiven for not knowing the name of the astronomer. That's Vera Rubin, who is the
Thank
one.
you. Thank you.
Yeah, he's the astronomer who discovered the incontrovertible proof of dark matter by
Yes.
measuring galactic stellar rotation.
You do that and they name an observatory after you.
There you go.
Yeah.
There's another telescope that's coming online at some point, the Nancy Grace Roman, and after another
Yes.
female astronomer.
Wait a minute, is that in space?
Yes,
Yeah, that's one in space. Yeah, that'll be named after a lady astronomer, and it's going to be, a new technology, a really good one.
ladies.
Any questions for Bill? All right, well, we thank you so much for doing it at the last minute, Bill.
I got one more.
Oh, another question.
Or just, yeah, a question.
You're welcome. My pleasure. I'm glad I was able to assist.
Well, Bill, at the beginning of your presentation, you were talking about how they put aluminum on a mirror. And I missed some of the details. Was that some kind of deposition? Or did they have a piece of aluminum that they,
It's a vapor deposition.
it is vapor?
Yes.
So
He said it better than I did. Vapor deposition. It's in a vacuum chamber. They heat up the aluminum, creates a vapor, and it just sits down on the mirror.
just like how they make
Plasma
chips.
vapor deposition, not chemical vapor deposition. The two of them are very different. One of them you don't want to get close to or cream your coffee with it.
Well, I was just wondering how thick would that piece of aluminum be? Like, is
But what
that,
I was told, it was just a couple of molecules. Now, what does a couple mean? 10, 50? I don't know, but not much.
yeah, awesome. Okay, thank you.
You're
Um,
welcome.
I'm curious if there's anybody online or in our in-person audience who has ever ground your own.
Ah, yes.
Yep.
Damn,
1970.
awesome. I am impressed.
I got one to an F5 curve before I broke it.
Have you done that, Bill?
I coded mirrors.
You coated mirrors. Oh, very
Yeah.
cool.
Some of them.
Yeah.
Anybody online?
I've never had the pleasure.
Yeah. I just would have thought that'd be impossible, but I guess not.
Wow. That's cool. Yeah, all kinds of books about that from the old days.
Awesome.
Yeah, that's how it was done back then. If you had one, it's because you made your own.
Exactly.
In the 80s, I was living in Chicago. Adler Planetarium, a huge, fantastic planetarium, had their own mirror grinding lab run by a guy whose name escapes me right now. And he was a master craftsman, made great mirrors, and would teach people how to make them. And when obviously with Celestron and Mead and other companies, mirror grinding, it was kind of disappearing, becoming a lost art. The planetarium decided to close the mirror lab down, and a lot of people were not happy. They saw the history going away, if you will. And but that's things change, right?
When the Austin Company was started, there was a guy by the name of Hoy Walls. And Hoy would hold telescope making workshops at the Austin Natural Science Center. And had a friend of mine from high school that was grinding a 4-inch mirror. That's kind of how I got introduced to it. So
Awesome.
it was back to our beginnings.
So
I'm
really,
really glad that other people did that, and I'm really glad that I didn't have to.
I'm curious about the lost art of grinding a
Yeah.
reading lens. You don't see anybody doing that.
No.
Not when you can buy a C Star for $400 or $500, et cetera, et cetera.
Charles, is there a comment on the chat? I see a,
No. Let's see what's on there. No,
Oh.
just a thank you.
Just thank you.
okay. Well, I guess we're.
Thank you.
Okay, thanks, Bill.
You're welcome. My pleasure.
Can you hear us applauding over here?
Oh, yeah, it's deafening.
Awesome.
Thank you. Thank you.
We
Oh,
I
are very
appreciate it. I appreciate it.
It's been half a late.
awesome. Okay, well, actually, I meant to tell him, or maybe still, oh, good. We normally, treat the person who, the guest speaker to, burgers and beer or pizza, beer, or whatever we happen to find nearby. But, sorry, Bill, we'll just have to have some for you.
I'll take a rain check. Thank you very much. Don't worry about it.
We would love to do, cash in that rain check, visit us anytime. So I guess that wraps up the meeting and we're early. That's awesome. And typically we do get together lately over at the Crown and Anchor, for, burgers and talk and, Joyce and I were debating about, whether it will be more busy because it's the beginning of spring break or less busy because it's the beginning, because a lot of folks are going out of town. I will say a lot of the students in my classes are going to be spending the week studying. I'm impressed. They're very studious. So I don't know anybody that's partying, but I do know there's a lot of folks going out of town. So, take your chances, but I would, y'all interested in heading on over there. Actually, we got some more pie to finish up.
Anybody wants to get pie to take home, please, because there's still a lot left.
Lots of pie.
I'm good.
Yeah. Because, I'll have to take a little bit of the pie. So I guess that's it. Thanks, everybody. Unless anyone has any, comments, anything to add? Do we have some more visitors that came in later? Are you a visitor? Way in the back. Yeah. Hey, are you a student?
I was, yeah.
Oh, nice. Well, welcome. What's your name? So I can put you on the spot. Fatima. Welcome. I'm Jamie. Just join us and it's Pie Day, right? So that's why we're doing this.